Yeah, Christina, no problem. I will stay after class so you can ask me about homework. Sure. Okay, we're ready. These are the instructions for the final exam. I will show it again on Wednesday. I just want you to know that the first question is going to take you longer than the second question. That's why I'm giving you hour and 20 minutes. And the second question is going to be the bonus. And there's going to be an overlap for people that finish the first problem earlier. They can, at 10 after 4, they can download the second question. And the exam is supposed to end at 4:50. I'm going to give you until 5 o'clock to upload all your uh, exams. I want to remind you that one of the biggest problems that we had last time was that your files, you were taking pictures, your files were just too large. It was difficult for you to upload it to Blackboard and you panic. So make sure that you use a good scanner and it has to be a PDF so I can write on top of your exam, I can grade it. So make sure that you upload your exam. Do not email your exams to me. You have plenty of time to upload your exams. And if you email your exams to me, for every minute that is late, I'm going to take 20% off on your exam. So make sure that you plan ahead and upload your exams to the Blackboard folder. Also, the maximum number of points that you're going to be able to obtain is 150 over 100. And just in case in the exam is a week from today, the bonus, the bonus is going to be a deflection or a rotation. And the reason is that in the previous exam, you didn't do that good with your deflection or, well, deflection especially. Right? So it's going to be either a deflection or a rotation. That's going to be your. Any question before I continue covering material today? Any question about anything? Okay. Well, you have any question, you let me know later. This is a typical frame that doesn't have what we call side sway or lateral movement. And in this particular case, we do not have lateral movement because there is symmetry with the loading and the geometry. By the loading, I mean this P goes to the right, this P goes to the left, and they're the same location, H over 2. And this load P is exactly in the middle. So there's symmetry with the loading. and also the symmetry with the geometry. That means this frame, it had a fixed support at this location. It had also a fixed support. It had a column that is H. It had a column that is H. It had a beam that is exactly between them that is L. So for us to determine by inspection if there is lateral movement or what we call side sway or no, we have to look at the loading and the geometry. I'm going to show you the first case of lateral movement. This is what we call a frame that is not braced. And this frame, they have lateral movement. There is symmetry with the geometry, like before, it's fixed, but there's no symmetry with the loading. So it's obvious that this frame is gonna move to the right. Whenever it moves to the right, it bends the column. It bends the column and the beam just move along this line. So there's a translation for the beam. So this delta at the top of the column and this delta are the same. And this delta, they're going to introduce moments into your frame. So we're going to have moment produced by the given loading and moment produced by delta. And this is a typical case that we have seen before. This case at the bottom of the fixed end moments table, this is a very important figure because it shows that without load, we producing moment because we had a deflection, a movement, the support. This support B was at this location. It had moved down in amount delta and had created moments in the opposite direction, 6 EI delta over L squared. So this is exactly what happens in here. This delta is going to produce moment. The column move clockwise, the moment go in the opposite direction. And there are 6 EI delta over L squared, 6 EI delta over L squared. The same happened with this column. This column moves in the clockwise direction. The moment go in the opposite, 6 EI delta over L squared, 6 EI delta over L squared. This girder of the beam is not getting any moment because it's just being translated. So there's no bending in here. So the moments are very similar to what I was saying in here. The delta or the lateral movement is producing moments in the frame. Here below, we had a frame. Obviously, there's no symmetry. Why no symmetry? Because this column is shorter, this is larger, much larger. So there's no symmetry with the geometry. And there's no symmetry with the loading because we had this and this. So the way this is going to deform, the frame is moving to the right, creating delta, and delta at the top of the column. What I want you to understand since today is that this high is different than this high of the column, and this is different. So since the moment this is the column, is the moment at 6 EI delta over L squared, 6 EI delta. This is L. So the moment depends on the value of L. So when we look at this member, we have 6 EI delta over L squared, 6 EI delta over L squared. The same here, 6 EI delta over L squared, 6 EI delta over L squared. The same in this one. In this one, there's a difference. This is fixed, and this is spin. So for the last one, pin or roller, the moment is only 3EI delta of L squared instead of being 6. My question to everybody is this. If I decided that this moment in here, 6EI delta of L squared is going to be 100, 6EI delta over L squared is going to be 100. So I'm assuming this moment in here. I know that 6EI delta over L squared, they go in the opposite direction than the movement of the column. So they go in the opposite direction. This column goes clockwise, they go counterclockwise. For anybody, the moments in this column are also going to be 100 or different? Anybody, yes or no?
Different.
Different, good. But just type. Thank you. So the same is going to happen with this column. So the moments are going to be different. In the previous problem, in here, the moments are going to be the same. Whenever we're going to solve a problem in the future, we need to ask if there is lateral movement or not. Because if there's lateral movement, there's going to be additional moments that have to be considered. So, do we have a symmetry with the loading in here? Anybody, yes or no? Symmetry with the loading. This is the loading. Yes, that's right. What about the geometry? This is one column, this is another column. Do we have symmetry with the geometry? Do we have symmetry with the geometry? Look at this and look at this. No. Because there's going to be a moment at this support, there's not going to be a moment at that support. So the answer for this is yes. There is going to be a lateral. So how do we handle this problem with lateral movement? This is the same problem. Look, fix a pin, there is going to be a delta. So whenever we had a problem that had lateral movement or side sway, we're going to have two moment distribution. One moment distribution, no lateral movement. Since it's moving to the right, we create a load that we call a P that is going to stop the lateral movement. So the very first, this is going to be moment distribution number one. No lateral movement. We're going to compute what is the force that we need to find this force P. And this is very simple because whenever we finish with the first moment distribution, whenever we finish with our table for moment distribution, we're going to have moments at the ends of all these members. Those are the moments that we use to plot the moment and the shear diagram. The only one that's not going to have a moment is going to be this. So with these moments in the column, we're going to compute the shear force at the base. You're going to see that later. And we're going to do summation of forces in X with the shear force at this base. And the shear force at this base, we're going to find P. After that, we have to put P into this frame and do our second moment distribution. But if you look at this table, if you look at this table, and if you have tried to solve your homework, you know that in order to solve this problem, we have to have a fixed end moment. And the majority of the cases, in order to have fixed end moment, we need load in the span. We need load in the span. You can see that we need load in the span. Load in the span. So all these tables, there's not a single case of our loading. There's not a single case in here that will allow me to put P in here and create my fixed moment for the second moment distribution, the one that had the lateral movement. But since we know whenever we had a delta, we know they're going to create moments that go in the same direction, opposite to the movement of the girder or the cone. And not only we know that these moments are exactly of the same magnitude, and each one is 6 EI delta over L squared. And the same happening here. We don't have any load, but we had a delta, we have moment on this end, 3 EI delta over L. So what we do to solve this problem, we're going to assume the moments in here. And since these moments are the same, I'm going to assume that this is 100 and this is 100. But in here, it's not going to be 100. If you look at this table, it's 6 EI delta over L squared is 100. 3 EI delta over L squared is what we had in here. So if this is 100, what is this going to be? One is 6 EI delta over L squared. And this is only 3 EI delta over L squared. 50, yes, 50. And we're going to compute it later. What I want to show you is that our second moment distribution is going to have this. It's going to have this moment, because to do a moment distribution, you need fixed moment. So whenever we finish, we're going to be able to compute the shear force in here and the shear force in there. We're going to do summation of forces in X. We're going to find this force Q in here that is different than P. But we're going to say if Q is producing all this moment, what will be the moment produced by P? So in order to find all the moments, we're going to add the moment from moment distribution number 1 plus the moment distribution number 2 multiplied by the ratio of P over Q. So we're going to see that later. This is the way we treat this problem. I'm going to show you in a little while a problem. We need 2 moment distributions. If we don't have a formula to put P, we have to assume this moment is going to give us a Q. And we're going to add the moment from moment distribution number 1 plus the moment from moment distribution number 2 multiplied by the ratio of P over this Q value. I'm going to show you the situation. This problem here on the top, I have no dimensions. We had a fixed support, pin, and a roller. How many unknowns do I have in here? Look, 3, 2. How many unknowns in this problem? Anybody? How many? 9. That's correct. And we had 3 equations. So 9 minus 3 is 6 degrees of indeterminate. So our first conclusion is that this structure is indeterminate. First conclusion. The second conclusion is, do we have lateral movement or side sway? So side sway, yes or no? And there's only one answer in here. Do we have a lateral movement? Yes or no? For this frame, is it gonna sway to the right or to the left? Anybody? Yes, and that is correct. So now we have to look at structures and count the components of the reaction, indeterminate. And the second question that we need to ask ourselves is, do I have a lateral movement? Yes or no? I'm going to make one change. I had changed this support. Now this support is a pin, no longer a rod. The same question, do we have lateral movement or, or sway or side sway? Yes or no? Yes or no? No, no, because this pin is not going to allow it to move to the right or to the left because a support in here had a constraint, vertical and horizontal. So no matter how strong you push, if this is a pin, it's not going to move to the right or to the left. So the answer in here is no lateral movement. So this is what we have to do. We have to look at very carefully. So this is the very first problem that we're going to solve. In this problem, we have symmetry with the geometry. Why? Because this is a fixed support, and this is A and C. They are fixed support. This column is 20, this column is 20, and this is 20 feet. So we do have symmetry with the geometry, but we don't have symmetry with the loading. This force is going to try to push this to the right. So the same question, determinate or indeterminate, counting all the possible components of the reaction. Determinate or indeterminate? Indeterminate. And do we have lateral movement? Yes or no? Okay, look at this curve. Assume that you had here Superman or Superwoman pushing this here. Is this column and this column going to move to the right? Look, if you pushing this, is this going to move to the right? Yes. So there's going to be a lateral movement. This will deflect something like this. So this is creating, this force is pushing the frame to the right. So it's creating a delta here on the top and on the top. So there's lateral movement. We're going to break this problem into two problems. Whenever we have lateral movement, we're going to break it into two problems. The very first problem, will have all the loading. So we're going to copy this frame. So we're going to put a force to stop it. So we creating a force P, no lateral movement. Will you be able to go over it when it doesn't have sideways? Yes. Whenever we don't have sideways, it's everything that we done up to today. For instance, You have to answer the question from Carl. This is what we did last week. Look, we had lateral load, the wind. The wind is going to push this frame to the right. Now, is this end going to move to the right? Carlos Garza. Look, this is a pin. If I push with everybody in the class, today we had 40 tons in pin. Right? So if everybody in the class pushes it to the right, is this going to move to the right, Carlos? Yes or no? Yes. This support will not allow it to move. If this were a roller, it will move. So there's no way. This one that we did last week, we had no lateral move. And I'm gonna try to help you in a little while. But this is why you were asking, no lateral movement, it cannot move. So I'm gonna go back to this problem and later I'm gonna come back and help you. So we were saying that obviously because of this force is pushing my frame to the right, there's the frame, there is a delta. Our first moment distribution has all the load, every single load that is in the frame appears here. No lateral movement. How do we stop the lateral movement? We put a force P, and we're gonna compute it later. In addition, we need to put the same frame. The frame moment distribution to size. So I'm gonna let this move. But how is it gonna move? Doesn't have any load. How is this going to move to the right? I had to put a force. And if I could, I would put P, but I can't because there's no formula. Indirectly, I'm gonna put moment, but indirectly I'm saying this. I'm putting a force Q at that joint. And that is gonna do this. I'm putting a force Q, it's gonna produce a lateral movement. But this delta is different than this delta. This delta in here is delta 1 because it's different. Anybody that wants to help me? Why this is different than the other delta? Well, I'm going to help you. It's different because for me to obtain this delta, I had to put the force P. But I don't have any formula that I can put P. However, I know that based on what I have in here, this moment and this moment are the same and they're equal to 6EI over 24. So look, this moment in here and this moment, they are equal and opposite to the movement of the column. This column move into the clockwise direction, they go opposite. And each one of them is 6EI delta over L squared. Where do I get this 6EI delta 1 over L squared? Where do I get this formula? Where? Where do I get this formula? How do I know from the chart, right? So I'm going to assume that this is 100. So this is 100 and this is 100. And since delta in this problem, delta 1 is the same and h is the same, if these are 100, these are also 100. So these are my fixed end moment, from for my second moment distribution. So I need to combine this effect. So I'm going to have moment distribution number 1. For my moment distribution number 1, do I have fixed end moment for column AB? Do I have fixed end moment for column AB? Yes or no? Do I have to start my moment distribution, I need a fixed end moment. From A to B, do I have fixed end moment? Yes or no? I have 2 yes, and we're not voting. There's only one answer. In order for me to have fixed end moments, I need to have load. I need to have load in here. Do I have any load between A and B? Do we have any load between A and B? No. No fixed end moment. Between B and D, do I have a load between B and D? Yes or no? Yes. And so the moment here on the left, MBD is going to be WL squared over 12. The moment DB is going to be WL squared over 12. What about between D and C? Do I have fixed moment? No, because no load. My distribution factor, whenever I do my computation, at A, it's going to be 0 because it's at 6, 0. And look, when I compute my moment distribution from B to D, for this entire problem, this is going to be 4EI over 20, 4EI over 20, 4EI over 20. All of these stiffness are the same because there's a fix, there's moment here, there is moment here. There is moment here, there is moment here. There is moment here, and there is moment here. So all of them, therefore, EI over L, it happened that L is 20. So when I do a joint B, when I do my distribution factor from B to A, it's going to be 4EI over 20 over the summation of 4EI over 20 plus 4EI over 20. So when I compute my distribution factor from B to A, what is that value going to be if those two are the same? What is the value for the 0.5 and 0.5? 0.5 and 0.5. That's good. All right. For my second moment distribution, these are my fixed end moment from A to B. What is the sign? What is the sign that I need to put to this moment? Positive or negative? When I go to my table for my moment distribution, this and this, minus. What about between B and D? Do I have fixed a moment between B and D? Do we have fixed a moment between B and D? Any fixed moment? No. And I have between D and C. And they're going to be also negative. Sometimes it's not that obvious which way the frame is going to move. Sometimes it's not that obvious. So if I assume that goes to the right and P comes with the opposite sign, means that goes in the opposite direction, all that I have to do is reverse the sign of this moment. Sometimes it's not that obvious. This is the same problem. But I already asked you about the fixed moment. Here is the computation. For moment distribution number one, W L squared over 12, the one from B to D, negative. The one from D to B, positive. Why the 20 in here? Look, I forgot to ask you. Why is this 20 not producing a fixed end moment from my first moment distribution? Why this is not producing a fixed end moment? Anybody? Why I don't have a fixed moment for this axial law? It's not in the span, doesn't produce anything, but we take it into consideration here. So for my first moment distribution, I already asked you to 0.5, 0.5. And for my second moment distribution, we already decided this is L squared, 100. So I want to create a table. For the final exam, if I give you a moment distribution, I'm going to give you the table too, so you will save time. So for the final exam, listen carefully. If I give you a problem like this, I'm going to give you the table. The table going to be in front of you. So you need to download the table or copy it from the screen. So this is the table. Look. I join A. I have one member, AB. I join B. I had two members, BA and BD. I join D. I had two members, DB and DC. And I join C. I have one member, CD. Distribution factor, AB 0, BA 0.5, BD 0.5, DB 0.5, and DC 0.5, here 0. This is what we had in here. Fixed moment minus 40 plus 40. For the second moment distribution, fixed moment 100. But what is going to be the sign that I need to put for this problem? Is positive or negative? For this moment, negative. I'm going to put a minus. So this is the table. So if this were the exam, you will get a table like this. You just need to put distribution factor. Help me to fill out this table. What is the distribution factor in here for AB? Alfredo? Yes, 0. What is adjoint B, BA and BD? What is the distribution factor in here? 0.5 and 0.5. What about joint D? What is the distribution factor here and here? This is also 4EI over 20, 4EI over 20. So the distribution factor in here, point 0.5. Not necessarily every problem is going to have 0.5, 0.5. In every problem, if this is 0.3, this is 0.7. If this is 0.6, this is 0.4. At each joint, all of this equal to 1. I'm from city 0. I'm going to do my moment distribution number 1, no lateral move. So I only had BD and DB minus 40 and plus 40. 0, 0, minus 40, plus 40, 0, and 0. So if you look at this table, I don't have any load, AB and BA 0. BD, I do have a load, minus 40, DB plus 40, and in here, no load 0. I had several people asking me the same question during the week. No. Joint B is not in equilibrium. We are back to what we did last week. It's not in equilibrium because the summation of moments at this joint is not 0. This joint needs, the entire joint needs a plus 40. Why a plus 40? Because minus 40 and plus 40 equal to 0. So I need to give to this joint a plus 40. 50% will come to here, 50% to here, and whatever I put in here, the carryover takes to the opposite end 50%. Or I can start with this joint. I can start with this joint. It makes no difference. It's not an equilibrium. This joint, I have a plus 40. I need to give a minus 40. 50% comes to here, 50% to here. I'm going to start with this joint. No reason why I'm starting at that joint. So when I start at this joint, I have a minus 40. To the joint, I need to give a plus 40. 50% comes to here, 50%. So that means, even with a calculator, plus and plus. What do I need to put in here? What number? Without a calculator, 20. 20. And since that is in equilibrium, that means that the joint has been put in equilibrium. That means that the joint has been balanced. But since I'm putting 20, immediately 50% of the value goes to the opposite end of the member. We put a little arrow plus 10 plus 10. The reason we are doing that, is because we have 4EI over L. Because if I had 3EI over L, you know that nothing goes to the opposite end. I'm going to look at this joint D. Joint A, fixed support, always an equilibrium. Joint C, always an equilibrium. Right now, I had a this joint, not necessarily because it's on this side. I had to put everything on DB. This is the joint D. I have plus 40 plus 10. Right now, I had a plus 50 to do summation of moments equal to 0. I need to give to this joint an equal and opposite, minus 50. 50% comes to this side, 50% comes to this side. Without calculator, give me those numbers. Minus. and immediately I balance it. Whatever I put in here, I need to send 50% because the carryover factor, using 4EI, minus 12.5 minus. When I put a moment to this joint and rotating the joint and moving the joint because we assume the word fixed is not fixed. That's the meaning of this moment. Look, A always in equilibrium, fixed support. C always in equilibrium. D is already in equilibrium, this means balance. The only joint right now that is not in equilibrium is B. I need to send to the entire joint a plus 12.5. And even if your calculator is broken, that is 6.25. Equilibrium. I need to send 50% across to the opposite end. 3.125. Okay, so I'm going to stop. We need to continue with this joint. You need to continue until you get to point one. I'm going to give you the final moment because I want to continue with the problem. So you need to finish this problem. As a matter of fact, it's already finished for you in the notes. In the notes, it's already finished for you. I'm going to copy the moments in here. So look, the problem is not finished. You need to continue or look at my notes. What I want to show you is that these are the final moments. And there is symmetry. When I did this, there's symmetry. That's why this moment came very close. I need to copy this moment. These moments are on the columns. So I'm gonna show you here. This is what I'm doing right now. So I'm gonna put on this column the moment because I want to compute the shear force. So I'm gonna look in here how you help. AB 13.32. AB, I need to put it in here. Is it gonna be clockwise or counterclockwise this moment? AB in this column. What direction? Clockwise. So I'm gonna put it here this moment. I'm gonna call it 13.32. On top of the column, I have BA 2664, also positive. So I'm putting the moments on top of the column. I'm going to go to this column. I'm only interested in the column. DC 2666 negative. And from CD 1333 negative. So from the first moment distribution, I'm putting only in the column the moment. Any question about that? Any question? And just from the first moment distribution, I'm putting the moment in it. What I'm doing that because now I want to do this. And I want to warn you, if I had a horizontal force in here or any type of force, I need to put it in my free body. This is my free body. So from column AB, I had a moment. Column AB 1332 and BA 2664. These moments go in this direction. I'm going to put a 420 also. My horizontal force in here has to go to the right or to the left to be in equilibrium. The horizontal force to the right or to the left. Here. There's only one direction. These moments are going in this direction. So to put in equilibrium, to the right or to the left? To the right. AX. How do I compute AX? I apply moment about this point. Because I want to get rid of that 20, apply moment about that point. If I apply moment about that point, it's going to be AX times 20 minus 13.32 minus 26.64 equal to 0. So from here, AX is equal to 13.32 plus 26.64 over 20. So I'm finding AX and applying moment about B. And that force in there became as 1.99A, almost 2. Right? So this force, I'm going to come back to here. I'm putting this force in here, the same direction, 1998. So I want you to do me a favor. For this column, do the same and tell me what is the shear force and the direction that you have in here. Anybody do the computation for this column the same way that I did in here and tell me what is the shear force in there and the direction. So you need to add this number plus that number divided by 20, give you the shear force in here. Give me the magnitude and the direction, right or left in here. So you got 2666 to the left, that's correct. And the magnitude? Same magnitude. Good. So I'm gonna do summation of force in X for this frame. I'm gonna have 1.998 minus 1.998 plus 20 minus P equal to 0. We call this the shear equation. This value minus this value plus 20 minus P. What is P equal to in here? If you look at this, 1.998 minus 1 plus 20 minus P, 20. And if you are observant, it was expected. It was expected to be 20 because we have symmetry. It was expected to be 20. But what we had, this is the final moment per moment distribution 1. So these are all the moment produced, but I have to do my moment distribution too. I had to do moment distribution too. So I start with the fixed moment. For moment distribution, how do you get P again? With this moment, we found the shear force. With this moment, we found the shear force. So for the entire frame, I'm doing summation of forces in X. 1.98 to the right, positive. 1.98 to the left, negative. Plus 20 minus P equal to 0. From here, P comes to 20. I'm doing summation of forces in X, or what we call the shear equation. Christina, you, okay. So summation of forces in X. So I need to do my second moment distribution. For my second moment distribution, is the one that had the size weight 100, 100, 100. So AB 100, BA 100, DC 100, CD 100, and nothing else. So this is my table. I'm going to use the same table because the joints are the same. The members are the same. The distribution factors are the same. The only thing different is the fixed end moment. AB minus 100. BA minus 100. BD 0, 0 minus 100 minus 100. So my second moment distribution, I was saying, joints are the same. Members are the same. Distribution factors are the same. The only thing different, fixed moment. Where do we get them? From our assumption, 6 EI delta over L squared. So I have put it in here. So we're going to start our second moment distribution. And you can start at any joint that you want. At joint B, we have minus 100. Joint A is in equilibrium. At joint D, we have minus 100. At joint C, equilibrium. I'm going to start at joint B. I also could start at joint D. At joint B, I have minus 100. I need to give to this joint an equal and opposite summation of moments equal to 0. So plus 100. 50% come to this member 50%. So that's why this is plus 50 plus 50. Equilibrium. I have balanced this joint that have minus 100. I put to the entire joint plus 100, distribution factor 0.5, 0.5. So I need to send to the opposite n plus 25 plus 20. This moment plus 100 that I put at the joint is rotating my joint. It's rotating the joint because the moment is going through a rotation. But I send to the opposite side plus 20. Now this joint D, needs balancing. Right now I had a minus 75. I need to put a plus 75. 50% comes to this side, 50% comes to the other side. So give me those numbers, please. Plus 37. And this line means that I have balanced my joint, put in equilibrium. 50% the carry over factor, take 50% to the opposite, 50% to the opposite side. And that 50% is 1870. Every single joint, equilibrium, equilibrium, this is no longer an equilibrium. And you have to remember, I have a plus 1875. The entire joint needs a minus 1875. And 50% of the value goes to the left, 50% goes to the right. And so, what is that value? 9.37. That means equilibrium. But the carryover factor will kick 50% of that value to each one of the opposite side. So 50% of that value is 4 point 9.375, 4.68. I put 4.69. So this problem is not finished. You have to continue with this joint. I'm going to assume that it's finished. So it's not finished. You need to finish or look at the solution. And we need to add every single moment in depth. And this is what it comes. So these are the values that we obtain when we add everything. These are the moments due to moment distribution number. So we come to our column like we did before. we come to this column. I'm going to write the moment for this column. So AB you look at AB minus 79.99, BA 59.90, DC minus 60, and CD minus 79.99. All of them, they go in the same direction. And all of these are negative. So what direction do they go? Clockwise or counterclockwise? I'm going to write them off. So from the table, I have put these are the moments that we get from moment distribution number 2. And I need to find the shear force. Look, this moment go in a kind of clockwise direction. My shear force in here and in here. What direction should the shear force go based on this column? What direction, to the left or to the right? This moment goes in this direction. To compute the shear force, add those two, add these two, and divide it by 20. Add these two moments and divide by 20. And tell me, what is the shear force that you have? So you add these two moments, divided by 20, divided by 20, we computed this reaction. Okay, 7. And 7. Now pay attention to this. I'm going to do summation of forces in X for the entire frame. Look, we have Q to the right, 7 to the left, and 7. So summation of forces in X, we have minus 7 plus Q equal to 0. So summation of forces in X, minus 7 plus Q equal to 0. What is Q equal to? 14. Yeah. So Q is 14. But look, and this is the most important step. For the given loading, I had a 420, P20, but I didn't. I couldn't put 20. I assume my fixed moment is 100, and it gave me a Q14. So to the moment distribution number 1 moment, I need to add this moment. But these moments are produced by 14. So if these moments are produced by 14, I only need the moment produced by 10. Look, oh, sorry, by 20. I need the moment produced by 20, this is by 14. So the way we do it is saying, if 14 is produced in this moment, what are the moments produced by 20? If 14 is produced in this moment, what are the moments produced by 20? So it's going to be, the X is going to be equal to 20 over 14 times the moment produced by 14. Again, and this is the most important step. Moment distribution number one, to stop the lateral movement, I had to put 20 kips. I didn't have a formula to put the 20 kips, so I assume moments 100, 100, 100. When I assume that, it given me moment that produce a 14. So what I had to do is to the moment distribution number one, I need to add a proportion of this moment. And the proportion is 20. So P over Q times the moment produced by Q. P over Q moment produced. So what I need to do, all of these moments in here need to be multiplied by the ratio of P over Q and added to this on the top. So I'm going to say here, P is 20, Q is 14. I need to multiply every single moment from moment distribution number 2 by the ratio 20 over 14. And I need to add those to this moment. So I did it the long way instead of using the table. I did it in here. Look, this was the moment from moment distribution number 1 plus the ratio between P over Q times the moment distribution number 2. So if you look at the table, this moment plus the ratio between P over Q times this moment, this is what I've done. Moment distribution number 1 plus P over Q, moment distribution number 2, give me this moment. From B to A, moment distribution number 1 plus P over Q times moment distribution number 2, give me this moment. For each one of them, moment distribution number 1, ratio P over Q times moment distribution number 2. Moment distribution number 1, P over Q for all of them. And these are the moments. These are the final moments. At each joint, equal and opposite. At each joint, equal and opposite. And here, below here, I have plotted the shear and the moment diagram with this back. I'm going to go over the whole thing right now. This is the first problem that we are solving, the head lateral movement. This was the original problem. And because we don't have symmetry with the loading, this is going to try to move to the right. Whenever we have side sway or lateral movement, we need to break it into two moment distribution. One, we know lateral movement. How do we stop the lateral movement? If this is moving to the right, we put a force toward the left. With a given loading, we're going to solve moment distribution number. But we need to take care of the side sway. But you know how I was able to compute P equal to 20. But I cannot put 20 into here, but I can assume, and I will assume this moment, based on my fixed end moment table. We know that 6 EI delta over the square 6 EI delta, the same thing. So my moment distribution number 2, I'm going to start with this moment it's going to give me a force Q. And after that, when I'm done, I'm going to add to this moment the ratio between P and Q multiplied by the moments that I obtained. And so this is reduced into a table. This table has two portions. One is for moment distribution number one. We started with all the load, W squared over 12, W squared over 12. We didn't finish, assume that was finished, and we found this moment. The only thing that we did, we put this moment in the column. We put the moments for the column. We don't need the one for the girl. And with this moment, we compute the shear force. We did a summation of forces in X and gave us the P equal to 20. We solved our second moment distribution. The second moment distribution, we start fixed a moment 6 EI delta over L squared. 6 EI delta over L squared. This one, they don't have any moment because it's just a translation. And with the second moment distribution, we put the moment here in the columns. And we found the shear forces. And with this summation of forces in X, and came the Q equal to 7. 14, sorry. But I don't have 14. I have 20. So to this moment decision number one, I need to add number two multiplied by the ratio P over Q. Number one, given loading. Number two, lateral movement. P over Q times each one of these numbers were added. And that gave us the final moment. This moment, take into consideration the lateral movement. And this moment, you just plot it in here. And you do your shear moment. I know that this is too much for a Monday. Any question? What if we assume Q toward the left? Okay, that's a good question. Normally, we're going to find out P. We're going to know the direction and the magnitude of P. So let's assume that I assume that P goes to the left. And before I compute P, I assume that this moment, because the movement of this frame, P is stopping a movement to the right. This is the movement to the right is producing negative moment. But if a different problem, P comes in the opposite direction, I need to reverse this moment. So this moment go in the opposite direction. So instead of negative, they're going to be positive. That's all that we do. But sometimes it's impossible. Q is obvious the direction. One, we know the direction of P. Any other question? And can we always assume initial moment? It depends. Look, I have created a problem that is indeterminate, and I'm putting a force. This is going to move to the right. So this is going to do this. So all the values of delta are the same. I'm going to assume that this one is 100. Since the movement is to the right, I have to assume that that goes to the left. 100, 100. So 6EI delta over 20 squared is equal to 100. Right? I'm going to find delta because delta is the only common number in there. So I'm going to find delta is equal to 100 times 20 squared over 6EI. So I had it here. Assuming this 100, 6EI delta over 20 squared 100. I'm going to do this one now. 6EI delta over 15 squared. Right? 6EI delta over 15 squared. The only common value is delta. I'm going to replace delta. 6EI over 15 squared times delta, 120 squared over 6EI. So what I had done, 6EI delta over 15 squared, delta is common for all of them. I replace the delta, 120 squared, 6EI goes. Tell me, what is the value? What is the value that you obtain from here? Do the computation. 100 times 20 squared over 15 squared. Are you sure? 177. Okay. So this is 177. Now I'm going to do the other one. The other one is 6EI delta over 10 squared. This one is 6EI delta over L squared. I'm going to replace delta like I did before. 6EI over 10 squared times 100 times 20 squared over 6EI. 6EI go. So tell me, what is the value? 400. Okay. Hopefully you didn't make a mistake. I'm making this up. So this is your answer. You could assume any of them as 100. I could have done this, I could make no difference. And so when we assume 100, we find all the others because delta is the same. So in this case, they are different. Now a question that they always they ask me, why 100? Right? 100 because this was invented in 1931, 1932, even before I was born. And remember, when I went to college, we didn't have calculators. We didn't have what you have today, only a slide rule. So in 1930, you needed a large number to have some significant figure. So they assume a large number. And by tradition, now we assume a large number, but it was based on the technology that they had at that time. But you can assume any number that you want. The only thing you have to remember, they had to be the same magnitude because 6EI delta, you can use 10, you can use anything. 6EI delta over square, they have to be the same. But sometimes whenever you use 10, the number comes too small. And that was the problem in the past. Now there's no problem because you have a super calculator that you can do as much as you. But traditional, it gives a large number to work. We use 100. But you can use any number as long as 6EI delta over L square and 6 delta, this has to be the same. Any other question? Okay. So we're going to continue. We're going to continue on Wednesday, but I want to repeat what I said at the beginning. Let me see something. Right now, we have still 40 of you left in here. I think before we can assume if there is a different support, you have to take that into consideration because, for instance, look, the same problem. Right? This is 20, this is 15, that this is 10. I assume this one 100, right? So now that we had a pin, this one is going to be 3EI delta over 10 square. Replacing delta, 3EI over 10 square, the same delta before, 120 square over 6EI. Tell me, what do you get from this one? 200? What do you get from that? The 200 or 800? So we put it here, 200. In comparison with 400, because the support is different. Any other question? Okay. I forgot what I was gonna tell you. Probably I will remember on when. Homework question. No, no, we use the correct formula for the given support. That's correct. Okay. All right. That's good. Yeah, Christina, let me put my notes together and I help you. From one question, just one. Okay. Let me, Christina, can you take over the screen and show me your problem number one? Can you, Christina? What number were we supposed to do for homework 10 due Wednesday? I'm going to show you again. Look, this is the homework problem that I had combined. So for Wednesday, this is what I want. 1, 2, 3, 4, 6, 7, 8, and 10. This is what I gave you last week. Yeah, you got right. 1, 2, 3, 4, 6, 7, 8, and 10. Yeah. Okay. Well, give me the. I need to look at your. Christina, can you take over the screen? Your room. Right. Okay. So if you cannot do it, let me see if I can get my homework number one. Let me get my homework number one. Don't worry. Look, this is homework number one. Right? The table. Check your table. You had this moment, Christina. Don't worry. Christina, are you there? My distribution factor. Oh, well, look. Everything here is 4EI over L. If you look at here, and there is a moment, because this is a continuous member. So there's moment at A, B, BA, BC, and CD. This is W squared over 12, W squared over 12. This is 3PL over 16, 3PL over 16. So in here, look, from B to A, 4EI over 24. I is 900. This I divided by 900, 1.33I. So 4EI over 24 plus 4E, 1.33I over 16. So gave me 0.33. What do you have? Yes, Derek, I'm having the review on Thursday. I don't know if we're going to start at 12 or at 11, but definitely we're having the review on Thursday. What time do you prefer the review? Just to give an idea. Okay, you're still thinking. Christina, do you see the distribution factor? The eyes are different. Christina, I forgot that they had different span length. Oh, 24 and 16. Okay, no problem. Any other question? Miguel wants on Wednesday. But on Wednesday, we're going to have also indirectly a review. But I think that we need to have more time because on Wednesday, hour and 15 minutes is not enough. So what time do you want on Wednesday, the review? All day. He's trying to kill me. So I think that Thursday is better. Oh, but I don't know. Yeah, I don't know if I'm going to start at 11 or 12. I will ask on Wednesday, but I'm going to upload the notes probably tomorrow night. I'm working on another review. Okay, guys, time to go home. Okay, well, see you on Wednesday. You have any questions, just let me know. I was going to tell you something important, but I forgot. I will remember later. All right. Bye. Yeah. I give you the answer next